The reason we study the Haber process is it's probably the most important chemical reaction in chemistry. I'd say the most important chemical reaction belongs to the biologist, it'd be photosynthesis. And what the Haber process does is allows more photosynthesis to take place. And so because this guy, Fritz Haber, who looks like Dr. Evil, was just trying to kill billions of people by getting more ammonia to make explosives, at the end of the day, the ammonia is being used to make fertilizer to grow more food. And so we've seen the Green Revolution and the increase in population by billions because we have plenty of food. And so this is the Haber process. Now, I'm just going to give you a brief explanation here, but because there's a lot of interplays between this, I have put out a computer simulation video, and I encourage you maybe to get access to that computer simulation, have a go, and if you can't, maybe watching the video will be useful enough. So what we're looking at here is the Haber process. Now the reason is that nitrogen bond is super strong, one of the strongest bonds there are, and it's very hard to break. And so we rely on enzymes in living processes to fix the nitrogen into compounds that NO3 and in here ammonia, to compounds that have more energy that can be used and broken up in living organisms. So it's unreactive here and we can't use it. And so what we need, what we've done here is we've created a chemical process that does it. And so the reaction is here. And so what helps this reaction occur is it's at equilibrium, but there is 4 moles of gases here and 2 here. So increasing the pressure is going to help it go in this direction, and also making it colder is going to make it go in this direction. Okay, so we'll just go for the easier one first, the pressure. So the high pressure will give a better yield, but that costs money. And so the system goes in here under a certain pressure, which is 200 atmospheres. And then if you go less than that, you'll get a lower yield. If you go higher than that, it just costs too much. Okay. The second thing you need to memorize besides the 200 ATM is the ion. So you need a catalyst that lowers the amount of energy that it takes. So the ion, generally a catalyst, it's, as far as collision theory goes, it's actually going to decrease the collisions. So the real effect of the catalyst is lowering the activation energy and the 3D orientation. So it'll line up the chemical in the correct way, or semi-break it or put stress on the bonds in order to make the reaction occur. And in the simulation, they suggest that it actually breaks the N and H2 up into little atoms. And so that allows the N2s and the H2s to react easier to get through. So it's increasing the activation energy rather than the 3D orientation. Okay, so once that occurs, you can see that the nitrogen here has a lot of hydrogen bonds, and so what you can see down here is its boiling point is much higher because it has much stronger bonds and the London dispersions between the H2s and the N2s. And so at this point here, it'll be somewhere less than minus 33, something like minus 50 degrees Celsius, to condense out and collect the NH3, and then the leftover H2s and N2s get reprocessed. Now, what's not said and what's helpful about the simulation is it's all about the money. It's all about trying to get the ideal conditions so it's profitable. And what's not said is that costs money as well. Okay, so if you've got to recycle it, you've got to reheat it back up to and repressurize it. Okay, well, I haven't done temperature yet, but you've got to repressurize it up to 200 atmospheres, so that costs money. And so let's go on to the temperature one now, because you would think that you'd want to decrease the temperature to also increase the yield, but it goes so slowly at a low temperature that it won't work. And so you can see here, as you increase the temperature here, you're decreasing the yield. All right, so that doesn't make sense, but the temperature makes the reaction occur quicker. And we don't care in the fact that we get a low yield because we're recycling it, yet we do care because it does actually cost money to reprocess it back up to 400 degrees Celsius and 200 atmospheres for reprocessing. So there's a delicate balancing act, which is why I think it's almost compulsory you should do that computer simulation to get a feel for all the different factors and then try and work out what the ideal numbers are. Because there's more than just temperature and pressure as well. There's also flow rates and all sorts of other things. How quickly this chemical can flow over the catalyst, etc. And for the contact process as well, there's exhausts and stuff. And so we heat it up so that the reaction can actually occur. And so 400 to 500 is the ideal. That allows the reaction to occur quick enough to get a product. I'll just make up numbers because students have had trouble understanding that. You might only get a 1% yield and it takes 1 second at this temperature. And whereas if you do it at, say, 100 degrees Celsius, let's say minus 100 degrees Celsius, which is still doable. Well, let's not make it condensing, so let's make it minus 20 degrees Celsius. You might get 100% yield or 90% yield, all right, but it might take a month, all right, and so it's just not going to happen. You're just not going to get product quick enough, all right. So we put the money in and to recycle it and get the reaction to work. So it's about 400 and 500 degrees ideal. A lot of that's to do with the fact of how quickly you process it and the fact that you're spending a lot of money to cool it down to get the ammonia out and then reheat it up and pressurize it to put it back through again. Okay, so hopefully you get that all comes together for you. I would memorize or put on your memorization cheat sheet for your exam, as I've suggested in another video on the exam page on how to prepare for the exam. 200 atmospheres, iron catalyst, 400 to 500 degrees Celsius.